You log into your reporting tools, expecting a clear view of your business health. But instead, you get a fractured mess. Revenue in one system doesn't match the billing metrics in another, and none of it aligns with your marketing spend. To see the full picture, you have to extract that data and centralize it. Doing so immediately introduces heavy engineering overhead. Software vendors market integrations as a straight line from source to dashboard. The reality is a chaotic mess of overlapping scripts and error loops. Choose the wrong architecture, and you end up patching the system while cloud costs accelerate out of control. Fixing this requires committing to a core architectural strategy that will dictate where your engineering team spends all of their time. Moving data involves two basic mechanics: extracting it from a source and loading it into a destination. But raw data is rarely ready to be analyzed. You have to transform it, cleaning the noise, standardizing the formats, and combining it into a structure. The sequence of these steps was established decades ago. When processing relied on physical punch cards, data had to be strictly formatted and sequenced before a machine could even read it. Early enterprise databases operated under similar physical constraints. Scarce computing power forced engineers to structure the data fully before the system could process it. Today, storage is cheap and cloud compute is massive. This forces every modern data team to answer two crucial questions. In what exact order do you run these steps, and how much data do you move at once? Answering these sequence and cadence questions incorrectly is the root cause of pipeline failure. The traditional ETL sequence, extract, transform, load, pulls data from the source, reshapes it on a separate server, and loads it into the destination. This makes your warehouse a secure vault. But this creates bottlenecks, and altering data permanently destroys the original historical record. The ELT alternative, extract, load, transform, dumps raw data directly into the cloud warehouse, using its massive compute to shape it later. You retain original data for AI and infinite query flexibility. But warehouse heavy lifting skyrockets compute bills, risking a disorganized, costly data swamp. ETL forces you to prioritize strict control and security upfront. ELT gives you raw agility and analytical scale. After choosing the sequence, you have to decide your cadence. The traditional method is the full data load, where you overwrite the entire target database from scratch, usually every night. Because you copy everything fresh every single time, you guarantee absolute data consistency with a very simple implementation. However, full loads waste massive amounts of compute resources. You crush the entire system with heavy processing just to update a few small records. Incremental loading takes a surgical approach. The system scans the source and moves only net new or modified records. Processing a fraction of the volume achieves near real-time synchronization, but it introduces fragility. A single dropped packet misaligns the database, requiring manual engineering fixes. Full loads trade processing speed to guarantee absolute reliability. Incremental loads trade stability to achieve near real-time synchronization. Executing modern ELT usually requires stringing together 4 separate tools: an extractor, cloud warehouse, transformation tool, and a reverse ETL tool. But every node is a failure point. API limits clash, syncs break, and the overhead to maintain the chain continuously multiplies. Artificial intelligence is now altering these pipelines. AI-native ETL agents can scan vast amounts of unstructured data and extract the context inside. These models auto-detect schema changes and interpret semantics on the fly. They recognize that a field marked delayed in an operational log is the exact same metric as a late delivery in a customer database. This replaces deterministic line-by-line scripts with probabilistic models. You are asking an AI to guess the right answer, which introduces entirely new data trust issues. As pipelines evolve from automated tasks to intelligent agents, the engineer's role shifts. You move from writing rigid rules to auditing AI probability. Let's map constraints to architecture. In regulated sectors, your constraint is risk. Choose ETL with nightly full loads to guarantee unbreakable compliance. If you manage massive unstructured data for AI, your constraint is analytical agility. Choose ELT with incremental loads for ultimate query flexibility. There is no universal best practice in data engineering, only the architecture that perfectly matches your constraints. Don't build a complex, real-time ELT pipeline just because software vendors market it as the standard. Match your pipeline's complexity strictly to the speed at which your business actually makes decisions. If your executives only check their reports on Monday mornings, a heavy Sunday batch load is perfectly optimized engineering.